Okay, hello grade 12, so I really hope this works. I'm going to go through this paper. Oh, that doesn't really help. This exam paper, it's the supplementary exam from May, June in 2024. I printed it out and give it to you in class, but I just thought this might help in terms of us getting to go through everything before the exams. So for this question, 1.1, it's got to do with Newton's third law, and you get asked this question a lot. Like, I've seen this question on 4 separate occasions, and how you recognize it is this phrase over here, action-reaction pair. Newton's third law is that when one body exerts a force on a second body, the second body simultaneously exerts a force of equal magnitude in the opposite direction on the first body. So, the trick of these questions is, this one says wait and book. So you need to work out which two bodies are involved. So I think it's obvious that the one body is the book, but if you're talking about weight, it needs to be the earth. The weight has got to do with the earth. So once again, we can immediately delete those two. The weight is always between a body and the earth. And so this question is talking about the action-reaction pair of the force between the earth and the book. And then what you do, so this question is earth and book. What you do is you simply swap the nouns. So instead of it being earth and book, it's book and earth. So if they had said normal and book, so the normal force, you should know, has got to do with the surface. So if they asked what's happening with the normal and the book, then the answer, the action-reaction pair, would be book and surface. You simply swap the nouns. That's all you need to do in order to answer a question like that. Okay, I want to see if I can cover this. Obviously not. Let me just do this properly quickly. Here we go. Sorry. Okay, so now for number 2. Number 2's got to do with a lift, which we covered in grade 11, believe it or not. I don't know if you've ever been in a lift, but if you can imagine yourself actually being in a lift. So step 1, we can ignore these two, because if it moves upwards at constant velocity or downwards at constant velocity, the acceleration is 0. So basically these two situations are exactly the same. So if the situations are the same in multiple choice, they cannot be the answer, because either both of those are right or neither of them are right, and you only have one answer. So now we are guessing between accelerating upwards and accelerating downwards. The answer is accelerate downwards. I don't know if you've ever been in a lift, you feel heavier when you're moving upwards than when you're moving downwards. But the actual reason is, when you're accelerating downwards, the acceleration and gravity are both in the same direction. So you accelerate less when you're going downwards, which means the force is less, which means you have a smaller reading on the scale. So basically, if it accelerates upwards, you will feel heavier, your weight will be bigger on the scale, and if it accelerates downwards, it'll be smaller. Okay, then next one. Okay, so the last one, number 3. I'll just see if I can cover this again. Number 3, it says the velocity time graph. Okay, and so now this is normally question 3. What we do with these is we work out that the gradients of the graph, or we know that the gradient of this graph is acceleration. The gradient of a VT graph is acceleration, and the area under the graph is displacement, always. So the area under the graph is displacement, and the gradient is the acceleration. They are asking what happened to the ball with this picture, and there are 4 different options. I don't know whether you can do any of them. I mean, if you can immediately cross out any of them, but the gradient of this graph is positive. The gradient of this graph is gravity, because this body is in free fall, which means down is positive. So here I have negative velocity, and here I have positive velocity. What's happening here is up, and what's happening here is down. So it cannot be dropped. If something is dropped, it moves downwards the entire time. It also cannot be thrown downwards, because if it is thrown downwards, it moves downwards the entire time. This example has some velocity that is negative, which in this case is up, because the gradient of the graph is positive, which means the acceleration of the graph is positive, and the acceleration is gravity, which is always downwards. So this part here is negative, and this part here is positive, which means this part is up, and this part is down. And if you look at the area under the graph, which is the other thing that helps us, this area is smaller than this area. So whatever it is, moved more down than up. So the movement needs to look something like this. It's more down than up, because the area under the up part is smaller than the area under the down part. So what they are describing is thrown vertically upwards from a height above the ground. Okay, so next up we have 1.4, which is for momentum, and we drew these in class. There were 3 examples of vector diagrams for momentum, and there was one that had, so P1 is like this, and then P2 is like this, which is the same as this one. What's happened here is my momentum has decreased. I used to have 7 momentum going that way. I now have 3 momentum going that way. So the change is -4. It's 4 to the left. That is what's happening here, and that situation is slowing down. That's what's happening. You also have a situation where you speed up. So the first one is small and the second one is bigger. So your first momentum is 4 and your second momentum is 7. The change is 3 in the positive direction. You have added 3 extra momentum. And I'm using the most ridiculous words, but it's just for us to understand the multiple choice question. We don't need to get values here. So this one, if the diagram looks like this, it's speeding up. All 3 of them are in the same direction. The initial momentum is in the same direction. So this one is in the same direction as that one, which is in the same direction as that one. You have increased your momentum, in this case with the imaginary numbers, from 4 until 7. In this case, you have decreased your momentum. It is decreased from 7 to 3. Again, just made up numbers. So the change in momentum is -4, and that is exactly what this diagram is here. If I can just highlight them, well, draw on them. That's the initial momentum. This is the final momentum. They are both in the same direction, but the change in momentum is in the opposite direction because some of the momentum that you had initially in the red has been cancelled out. That is what slowing down looks like. This one over here is what speeding up looks like. And then you also have this one where your initial momentum and your final momentum, whatever their lengths are in opposite directions. That means you have changed direction. So basically this blue one, so if this blue one is 7 and this blue one is 10, this green one will be 17. It cancels out all of the right and gives you left. So if you have this situation here, where the first one and the second one are both in the same direction, and the change is in the opposite direction, that is slowing down. Then you have all 3 of them in the same direction, that is speeding up, or you have the initial in one direction and the final and the change in the same direction. This situation over here is changing direction. You hit into a wall or something. So that's like you hit a tennis ball into a wall, or you hit a cricket ball into a cricket bat, and it changes direction. Okay, so then sorry, I haven't answered it. That is number 1.4, the momentum. So these two are changing direction. You were you had plus momentum and now you have minus momentum. So these two, you had minus momentum, now you have plus momentum. So those two are changing direction. It's not that. This one is speeding up. It's not that. We had slowing down. So it's A. And let me see if I can just get this thing to cover a bit. Okay, so that worked out all right. And now, this is a bit of a horrible one. This one has got to do with the stuff that we did in grade 10. This has got to do with mechanical energy. So what happens is a stone is dropped from a height. So at the top, this thing has mgh and half mv squared as its mechanical energy. It's how high and how fast. It always has how high energy and how fast energy. And it's like with the skateboarder, as its high decreases, its fast increases. So you have all of your high here and none of your fast. So at the top, normally your fast is 0 and your high is everything. But then when you get to the bottom, all of your high is gone, but it has all been converted into fast. So the energy that you had from being above the earth gets converted into energy that you're moving quickly. So the total mechanical energy, if you know the definition, the total mechanical energy in an isolated system is conserved or remains constant, which means that in the beginning, you had all of your high energy and none of your fast. So if we're guessing between C and D, because the mechanical energy must be mgh, because that's all of the high energy. And then they are telling you that the stone has fallen through a distance of a quarter h, which means it's sitting like over here, which means a quarter of its height energy is gone. A quarter of its height energy is gone. This much height energy has been converted into fast energy, which is why it says a quarter mgh. The 3/4 mgh is how much high energy it has left, but they are asking you for fast energy. 1/4 of its high has been converted into fast. Okay, so now for number 1.6, what we're doing is they're saying that the star is moving away from Earth, which you should know is a redshift. So moving away from Earth is a redshift. And if you know Roy-G-Biv, the low energy one, the low frequency one is the red, and low frequency means high wavelength. And the high energy one, the high frequency one, the low wavelength one is the violet. Infrared is on this side, which is a low energy radiation, and ultraviolet is on the right hand side, which is a high energy radiation. So a red shift means you're shifting towards low frequencies and high wavelengths, and so that kind of makes it easier. But if you were going to guess, they can't be lower and lower or higher and longer, because if they are on the same side of the equal sign, it means that they are inversely proportional. So when the one gets bigger, the other one gets smaller. When you're doing waves, if it's got a really big frequency, it's got a very short wavelength. If it has a really big wavelength, it's got a very small frequency. Frequency is how many waves per second, and wavelength is how long is each wave. So those are inversely proportional. So you can immediately exclude B and D, and then the other stuff, unfortunately, you would have had to study. So it's moving away from Earth, which means it's a redshift. If it's moving away, it's a lower frequency in Doppler effect, the nu. So the lower frequency sound happens when it's moving away. And so that makes you end up on A, if you know your Doppler effect things. Okay, now I'm just going to try and cover this thing again. Oh, Sherbet, sorry. Okay, so now you must come to front. And then we can look at the electrostatics example. So for the electrostatics one, we are given, this is an easy-ish one, I think. They are asking about E and Q. So you go to your formula sheet. Please don't use your brain, just use your formula sheet. and you'll find that guy, which has E and Q in it. So there's E and there's Q, and they are both on top of the fraction. So both the E and the Q are on top of the fraction, which means that they are directly proportional. And directly proportional looks like this. So basically they're just asking, is it directly or inversely proportional? So it's not that one and it's not that one. And because of the formula, which you are given on the formula sheet, you can see that it's directly proportional because the E and the Q are both on top of the fraction. And they are on opposite sides of the equal sign. So opposite sides of the equal sign, directly proportional. Both on the top of the fraction, directly proportional. If they're both on the same side of the equal sign, they're going to be inversely proportional. Okay, right, everyone loves to hate circuits. They are asking which of the ammeters has the lowest reading. So now we start at the battery and we follow which way the current goes. It doesn't really matter, but if I say that the current is 5 amps, for example, if I go this way, that A4 is going to be 5 amps, and so is A1. So both of those, A4 and A1, are not an option. They're both going to be, I'm just making up the number 5 amps, but both of them are going to be 5 amps. Then the current splits here. When it gets to this point here, it can either go that way or that way. So basically we're now guessing between A2 and A3. And the current that goes through A2, whichever way you go, doesn't really matter, whichever way you want the current to go, A2's current goes through R. A3's current, however, goes through R and another R. So A3's current goes through 2 R's. So A3's current has more resistance, which means A3's current will be smaller because V equals I times R. So for constant V, I and R are inversely proportional. The more the resistance, the less the current, and they wanted the lowest ammeter reading. So what you did here is you just followed the current, and I just made up a number, but you can, I think it's easier if you have numbers. So whichever way you feel like coming out of the battery, this current would be 5 amps, this current would be 5 amps, so it's not number 1 and it's not number 4. The current then splits when it gets to here, and it has a choice. If it goes through A2, it needs to go through 1 resistor. If it goes through A3, it needs to go through 2 resistors. So A3 has a bigger resistance in its piece of the circuit, and so A3 will then have the smallest current. And now, for number 1.9, I must just, sorry. Let's bring this forward. See if I can, there we go. Oh, except for that line for some reason. Okay, so now, this guy is what we just did recently in class, motors and generators. And just as a quickie, the motor takes electricity or electrical energy, and it makes it into mechanical energy. You take electricity and you make movement. A generator, you make the coil rotate, so you make something move, and what it does is it ends up making electricity. So a generator makes electricity. It's mechanical to electrical. A motor uses electricity. That's why you use your 2 different hands to work out the movement or the electricity. And in the diagram, you can see that it has a battery, which means you are using electrical. So immediately it's a motor. And if you can see here, there's a split ring commutator. That is for a DC motor or generator. So there's 2 separate things here that you need to see. The battery tells you that it's a motor, and the split ring tells you that it's DC. So this is a DC motor. Okay, so last but not least, we have, I'm just going to go through absorption and emission spectrums again. This question is asking you about an absorption spectrum, and an absorption spectrum happens when your light goes through a cold gas, and you end up with black lines on a colorful background. Emission spectrum it goes through a hot gas and you end up with colorful lines on a black background. For the absorption spectrum, energy gets absorbed by the cold gas, and so you don't see certain lines. They are gone. Energy is absorbed and they move up to a higher energy level. They move from a lower energy level to a higher energy level. For the emission spectrum, you have a hot gas and the energy levels actually drop down and they release energy which appears as certain colors. So these two spectra are exactly the same. The one just has black lines where the other one has colorful lines. The emission spectrum is with a hot gas and the energy transition is to a lower energy level. They move from a high energy to a low energy and they emit colorful light energy in certain frequencies, so you get certain colors. For an absorption spectrum, it's simply the exact opposite. It's a cold gas, and so energy is absorbed, and so you don't see those colors. You do see them through a hot gas in an emission spectrum, and you don't see them if you shine it through a cold gas in an absorption spectrum. So an absorption spectrum, it's going to be dark lines, so you can immediately delete B and D. And in this case, for an absorption spectrum, it's always lower to higher energy state. This one at the top, the higher to lower, is actually for an emission spectrum, which should be colored lines.